So today I want to talk to you about a couple of fields of AI that have grown not as fast as they should, given the impact that they're having on industry. A little bit about us first, and kind of go overview of the conversation today. I'd like to discuss the myth around AI, the magic, the models that we're utilizing, and some of the methodologies that we go about to execute on artificial intelligence, capitalizing predominantly on applied science through machine learning and then also computational physics, and the implications that that's had not only on our own industry of advanced R&D, but also industries across the world. So as we said before, we formed Valkyrie in May of this year. We've completed 11 programs with 9 clients. We've grown extremely aggressively. And that's due in large part to our commitment to science. First and foremost, we are scientists. We have backgrounds in nuclear physics, backgrounds in biochemistry, backgrounds in statistics, and even more canonical neural networks, which are associated with our field. Our portfolio, we get asked this question a lot, what are your major verticals? Well, the reality is that AI is a horizontal, not a vertical. So we are predominantly focused on our capability, and our capability happens to be applicable in many different areas, from biotech to automotive design to oil and gas to healthcare. We're all over the place. Fundamentally, we transform information to intelligence and intelligence to initiative. How many people in here are traditionally trained scientists? Physicists, chemists, biologists? Sure. This is nothing new. we use this for branding, but this is something you're going to be very familiar with. In fact, if you're a scientist already, then most of this will be review of some of the methodologies that you were exposed to when you were in middle school. Right? We are essentially taking the scientific method and using advanced techniques, new technologies, and complex problems in industry to bring real value. Our 2 primary disciplines are applied science, which we'll talk about a lot today. I lead the science discipline at Valkyrie. We also have a strategic services, and a lot of our strategists come from the Booz, McKinsey, Bain, BCG type organizations. This is not an advertisement for Valkyrie. I'm just trying to set some precedent about how we think about problems, I promise. Let's start with the myth, right? All that aside, you guys have some idea of who we are and who I am and what we do. Let's talk about the myth around AI. Almost everybody here, even the scientists and engineers, have something like this in the back of their head whenever they think about artificial intelligence, right? They try not to, we all try not to, but there's something about the lexicon that we've been exposed to as children and the media that we get excited about that has an unfair bias on what we think about AI, right? And so that's why we get excited about tools like Siri and Alexa, who try and replicate some of the fun functionality around the canonical artificial intelligence objects and people, creatures, machines. Of course, WALL-E is probably the closest, because why not? WALL-E's the best. But let's talk about the actual magic. Putting all of that aside, none of that's practical, none of that's real, none of that's brought any value to any company ever, anywhere. There are some things that are actually pretty exciting that are based off of some of the principles that we're going to be talking about today, predominantly applied machine learning. So who here has heard of Stitch Fix? Got some college students, probably a couple, sheepishly raising their hands, admitting that they know what Stitch Fix is at an AI conference. Stitch Fix is a retailer company that's dramatically changed the way inventories have been optimized for, and they've actually taken the whole shopping experience and turned it on its head. Using predictive algorithms, Stitch Fix has the capability of actually re-engineering the way you think about clothing, the way you consume clothing, by collecting granular detail about your behavior and matching that behavior to archetypes, matching those archetypes to different collections of clothing. That's pretty fancy stuff for a clothing company. Harley Davidson is another really interesting example of an excellent use of applied AI. How many people would associate downtown Manhattan with a Harley Davidson? Just about nobody, right? And neither did Harley Davidson, until they started running some complex algorithms that would synthesize leads and match those to motorcycles that they had within their inventory. And what do you know? It turns out that downtown New Yorkers love Harley Davidson. Their sales leads grew by over 2,900% by simply matching the right corpus, the right domain of users to the right domain of motorcycles. Nobody would have thought that was even possible. So these recommendation engines, I put these in air quotes because the term recommendation engine is loaded. What we're really talking about is matching two disparate domains across with a collection of ensemble classifiers and clustering techniques. That's really what a recommendation engine is, and has applications far outside of the way Target, Best Buy, Amazon uses it. And then the third example, you wouldn't believe it, but the best scientists in my field are all going to work for Match.com, OkCupid, oldfarmers.com or whatever all those dating websites. There's huge money in matching people to people, right? Huge amounts of money. And again, these recommendation engines, or multi-domain ensemble classifiers as we call them at Valkyrie, are incredibly important to understanding how two people should be matched to each other. What features do you collect on that individual? How do you monitor their behavior, feed into archetypes, and match those archetypes to other archetypes you identify in the space? Who here thought we were going to talk about Stitch Fix and dating websites? Probably nobody. What's the other thing that we notice about these three particular case studies, right? We're talking about optimizing products and processes, optimizing products and people, the three kind of core P's of applied science. How do we optimize processes? Well, we look at inefficiencies, we look at ordering, we look at procession, we look at propagation of certain systems, and we optimize those systems. How do we optimize for products? 20 years ago, products used to be optimized. People had to change themselves to use products. Now with persistent dynamic data and advanced algorithms, our products kind of have to adapt to people. No two people should have the same digital experience, and we're going to see more and more of a transformation towards that. It's one of the core pillars of what we do at Valkyrie. And then matching people in and of themselves. I'm getting pretty excited about where scientists are pressing us towards understanding individuals. It used to be that big marketing agencies and big companies would think about a human being based off of relatively antiquated terms, like the color of their skin, their age, their gender. But as it turns out, you can get a lot more out of a relationship with a customer by understanding just how they act, which has nothing to do with any of those antiquated properties. So matching people to people, understanding people, is one of the core tenets of artificial intelligence. And we're very happy to say at Valkyrie that we're proving day in and day out that those old antiquated phenotypes are really not that important to understanding an individual. So we took a look at what it wasn't. It's not HAL 2000. We looked at how it's actually bringing value to companies like Harley-Davidson. So why is there a huge delta? Why is Elon Musk, in all his infinite glory, so terrified about AI, as is Stephen Hawking, but Andrew Ng is not as much? Andrew's very excited, actually, about what's coming from AI. Kurzweil is in between the two. How are these experts so wildly misaligned with each other on what's going to happen with AI? That's because we have a fundamental definition of artificial intelligence that we believe is being missed by most of the community. We believe that most of the community is reading too far into the long-term implications of a field that's incredibly stochastic. This is not a deterministic system. It's incredibly probabilistic. So our definition, the objective of artificial intelligence is to extract context from information that is not explicitly stated. It's very simple. Some things out there can tell a story, but they don't inherently do that. They don't inherently help us make better decisions. They don't inherently help machines take the proper course of action to optimize for one system or another. Artificial intelligence is all about bridging that gap. And artificial intelligence has two very distinct fields, two very distinct subdisciplines. There's one that you hear about all the time, and there's one that a good chunk of you haven't heard about until today. The first is pattern recognition. And that's the art, the science, but partially art as well, of identifying patterns in innocuous data, making extractions that would be human valuable, and acting upon initiatives that can capitalize on those patterns that have been observed. And they fall into, traditionally, two different subclasses, unsupervised and supervised machine learning. You may be more familiar with terms like classification or clustering. These are relatively broad categories, and we could certainly have a whole semester-long course on each one of them. But suffice it to say, We use one when we understand the target, the feature that we're interested in trying to understand more about. That's supervised learning. And unsupervised is when we're not quite positive what that classification is, what that feature is like, and we're using machines to recognize patterns that are completely outside of our purview. And we also have a spectrum for how these two fields. Oh, I'm sorry. One thing I wanted to talk about is knowledge engineering. See, this is, I just mentioned that nobody knows much about it, and I just skipped over it. So about 95% of the market, more or less, is obsessed with pattern recognition. Right? How are we optimizing neural networks? How are we taking a hidden Markov model and employing it against 6 or 7 orders? Right? These are the questions and things that get published in Wired and published on all sorts of tech journals. But the reality is that knowledge engineering, the art of taking data and making it more amenable to pattern recognition, is a very underappreciated field. And yet that has the biggest implications on the kinds of patterns that we're able to identify. What do I mean by that? Data, by default, has to have a method for storage, a method for manipulation, a method for articulation. And that method is not always optimized for the kinds of patterns you're trying to elucidate from the data. Sometimes those patterns can exist in different ways across different domains, and you often have to change your data in order to represent that pattern as obviously as possible to the algorithm. Here's a real quick example. How long would it take, let's see, you have a volunteer. I like to be interactive. I hate just giving monologues. Any volunteers? Volunteer. How long would it take you to multiply 63 times to the 63rd power? A really long time, right? Super long time. We didn't need like scores of notebooks. How long would it take you, are you married? How long would it take you to recognize your wife if she was sitting in the back corner of the room facing the wall?
Less than a second.
Instantly, right? Is that because you're processing one system faster than the other? No, actually it's not. You're actually, your model for a number and your model for your wife are stored in wildly different ways within your neurons. And the synaptic firings that get you from point A to point B are wildly different. Now, a computer can do 63 to the 63rd power instantaneously, practically instantaneously. But I can guarantee you, I could train it with the most complex convolutional neural networks. I could use residual neural networks. I could use all sorts of different techniques, and I would have the hardest time figuring out if that was your wife in the corner of the room. And that's because the knowledge, the data, the information that we're storing in our brains around numbers is actually pretty akin to the way a computer stores numbers. They're very, very similar. And so the operations, the logic that we implement in order to get to 63 to the 63rd power is much the same as the way a computer does. A computer has way more processing capability, can do way more cycles, and so it gets there way faster. But when it comes to your wife, how is it storing that model? Right? We don't know yet. This is the exciting stuff. This is one of the big frontiers in science. I have no idea how you store the model of your wife that lets you find her almost instantaneously. No concept. We're working really, really hard to figure it out, and we're not making much progress. So computers can recognize patterns as long as they're well articulated in a domain that makes sense to them. And so the art of knowledge engineering is all about translating that data from relatively optimized for cost, oftentimes, formats into formats that elucidate all of those patterns that we just discussed. It's a really exciting field. Now, if you guys were to think about all the journals that you've read around AI and data science, you'd probably give 95% of your attention to this and about 5% of your attention to this. My conjecture is that those things should be reversed. We're getting tiny incremental improvements, going from HMMs to CNNs to RNNs to residual neural networks for image recognition, for example. Really tiny improvements, things that get people Nobel Prizes and all sorts of excitement. But the actual impact is really small. We're getting much better returns when we rethink fundamentally the way we store data. So the combination of those two subfields to create artificial intelligence, the applications of those fields sit on a spectrum. And that spectrum, the intelligence spectrum as we call it, kind of has 4 different classes. Descriptive analytics, predictive analytics, prescriptive analytics, or adaptive analytics, and intelligent systems. Examples of descriptive analytics may include Excel, for crying out loud, can be a descriptive analytic, right? Just stating the data as is. No extrapolation, no interpolation. Predictive analytics, taking a single value and creating a regression for the next value that comes in. Very straightforward. Prescriptive analytics, not only understanding what the next state is of a system, but adapting the system around it in order to compensate. An example of this would be, believe it or not, Netflix does a really good job of prescriptive analytics. Netflix not only understands the next selection you're going to make, but changes your environment. It actually changes the way you view other titles based off of the likely next step you're going to take. It adapts to your environment. Intelligent systems include Watson, all the aspirations of Predix, all of the new technology that's coming out of Microsoft Azure. I have a lot of thoughts on that, and this is a recorded session, so I'm going to keep them to myself. But suffice it to say that value, in general, starts pretty low with descriptive analytics, increases dramatically all the way up to intelligent systems. Intelligent systems, if they were able to be brought to fruition, if Watson was doing incredible things and not getting ripped out of MD Anderson for a loss of a $65 million contract, would have really big implications. Sorry, that was a subtle jab. I love Watson. Don't kill me. We also have confidence, right? Confidence in a particular system decreases aggressively as the system becomes more and more complex and more interdependent on ensemble techniques and deep learning and all sorts of complex algorithms. So confidence comes down dramatically. And then finally, the complexity of the system, in order to actually develop it, grows very, very aggressively. So descriptive analytics, not a lot of value, not very complex, but you have a lot of confidence. If you have a weather station at your house, are you going to challenge that it says 78 degrees on the screen? Probably not, right? But if we're looking at a model that's predicting the weather a week from now, you have a little bit less confidence in that system. You're not really sure. Weather guys get it wrong all the time, right? So this is really important to keep in mind, because there's a lot of hype and there's a lot of buzz around these intelligent systems. But as we spoke about earlier, that's not really where the huge value is coming. Huge value is going to Harley-Davidson, which has a great implementation of a predictive analytic, right? Really big, yes, a predictive analytic. Huge value is coming out through prescriptive analytics for Netflix and Uber, where they're actually adapting environments to compensate for the predictions that they're making across the entirety of an ecosystem. Not a lot yet is coming out of intelligent systems. And I personally contend that we won't actually get to a point where intelligent systems become valuable. I am not a doomsday sayer on AI. I don't think that it's going to take over the world. I don't believe in Skynet. There are fundamental nuances of the human brain that are still so elusive to us that the idea of creating a sentient machine is borderline preposterous. But it sure sells a lot of Wired magazines, so that's fun. So I'll breeze over these two subjects really quickly. We talked about it a little bit. We have unsupervised and supervised learning. Some of our favorite techniques in unsupervised learning are the hierarchical clustering and fuzzy C-means. Of course, K-means is a great favorite. If you're trying to get into this space, K-means is a really easy model to get into. In fact, anybody here take geometry at any point in middle school, right? Everybody? If you've taken geometry, then you're actually very familiar with the K-means, the K-nearest neighbor. It's the Pythagorean theorem applied across as many dimensions as you want. It's really, really simple. But it actually does a pretty good job. It's slow, but it does a pretty good job. Supervised learning is a little bit more interesting. There are certain neural networks that we use that are favored in a supervised space. Support vector machines are great. Random forests, oh my gosh, where do they come from and how do they take over the entire industry? There are hardly any problems that we don't at least run an RFR or an RFG against in order to try and solve a problem. They're really, really useful. Then we have the field of deep learning. I'm gonna go quickly over this. This certainly could be turned into an entire bachelor program or master's program. But suffice it to say, neural networks are all about extracting hidden nuances in operators without understanding a lot of detail about those operators. Anybody familiar with the hidden Markov model? In a lot of ways, there are significant overlaps with HMMs within neural networks. A lot of the structures, particularly for recurrent neural networks, is exactly the same as an HMM, but they're optimized in different ways. The way that they're able to integrate backpropagation, the way that they're able to reweight those hidden layer steps, it's different, but it's a similar concept. Believe it or not, of the clients that Valkyrie had or the clients that I had at Frog where we were developing these complex AI systems, almost never, really very rarely do we make recommendations that implement deep learning. That's shocking, right? Oh my gosh, it's the latest, it's the greatest, it's so cool. What couldn't we do with deep learning? There's a lot you can't do with deep learning. In fact, 9 times out of 10, deep learning is an answer that's going to get you into trouble when you're trying to develop a massively consumed product. So we worked with a big bank to help them develop their digital experience that relied on recommendation engines. Guess what we didn't use? CNNs for image recognition. Guess what we didn't use when we were trying to make predictions about risk for a private equity fund? We did not use a recurrent neural net. We used a hidden Markov model. A lot of that has to do with the fact that more traditional methods are still much more robust and safer when you're developing something that can be adopted en masse. So I rather have a model that has an R squared of 87.5 but uses an HMM than a model that achieves an R squared of 89.5 and uses some form of deep learning. That said, deep learning can be kind of cool. So here's one of my favorite things to play with. We love convolutional neural nets for R&D. We also love a relatively new field called residual neural networks that are both used for image classification, optimization, and eventually style transfer. So this is one of my favorite paintings. It's a Picasso called Seated Nude. And this is one of my best friends when he was off in a sandy place doing awesome things for America. And what happens when we break down this sample until the lowest geometric primitives that you can take, and then recognize those geometric primitives when they appear into a photograph. Right? The end result is the ability to superimpose the style of this painting upon this image. This was not retouched. This wasn't edited by any artist. This is literally a computer's interpretation of a Picasso and superimposing that upon a photograph. This code is actually accessible. We can share it after the conversation. It's really fun. And there are different ways you can tweak and optimize and really get a good sense of how CNNs and residual neural networks work. So we talked about pattern recognition, all the stuff that gets all the hubbub and buzz and hype, everything from SVM regressors all the way up to recurrent neural nets. I didn't do it any justice because they're incredibly large subjects in and of themselves. But I wanted to talk today about knowledge engineering, that field, again, of optimizing for pattern recognition within data. There are multiple different ways you can store data, as it turns out. And a lot of the decisions that were made 10, 15, 20 years ago to optimize for scale and cost aren't really the right decisions in order to optimize for pattern recognition and AI. So relational databases like MySQL, even Postgres, are optimized for certain types of queries, certain types of observations, and they're optimized largely for cost and scale. So it can be really performant with minimal architectural development. Document-oriented are a relatively new class of, actually relatively new in the way that they've been productized, but they've been around for quite a while. And this allows you to store completely unstructured data. Anybody heard of MongoDB? Kind of the big guy in the space, right? You've heard of MongoDB. You can have semi-indexed or completely non-indexed, completely unstructured data. And it lets you really write whatever you want. Who here's heard of Neo4j or graph databases? Less, but that's OK. Cool. I'm going to teach you something really awesome today. Graph databases are one of the most important technologies to gather attention and growth in the last 5 years. The particular tool Neo4j is invaluable when it comes to pattern recognition of complex spaces, networks, and relationships between different objects. So some definitions that you should take a look at and when learning more about the space: ontology, basically the spirit animal, if you will, of a database, right? What is it representing? What are the core identities? How are those identities related to one another? Taxonomies. What are the structures of those subgroups within the ontology? Topology. How are different domains or groups related to one another within that ontology? The architecture, of course, and schema, which is the really tactical implementation of that ontology. But this is all really abstract. Raise your hand if you know exactly what I'm talking about and you're good to go. Should be nobody, right? Let's talk about an actual example. Here's Keybar in the best city in all of Texas, the Republic of Texas, Austin, of course. Yeah, thank you. This is Keybar, a fun little place on 6th Street. And let's say your goal, we have a lot of college students, a lot of people in college age at least. Let's say your goal is to find your soulmate. You've got an hour and you have to find your soulmate before the bar closes. So I can give you 3 different types of data, right? The first type of data I can give you is everybody in the bar's police history and their driver's license. It's pretty valuable. You can get some information out of that. I can also give you the last document that they wrote in school, whether it's high school, college, whenever, right? That's also pretty useful. You can see if they're well-written, see the things that they're interested in. And I can also show you a network of how each of these individuals spoke to one another throughout the night, how much time they spent mingling with other people, and potentially some vectors or some values about the vectors of conversation. So we've got basic static fields, right? Static fields. If you're not following the analogy, we're talking about MySQL and RDBs, right? Or Postgres and RDBs. Any type of SQL database is kind of like a collection of relatively static fields that you can't really add additional information to. And then I'll also give you the last document that they wrote in college or high school. And then finally, I'll show you a network of how everybody's speaking to one another. Now, everybody here is industrious, intelligent, driven. I bet you can do a lot with this information. If you only had an hour before the bar closed, you would probably freak out to have all this data in front of you to be able to figure out exactly who you should propose to on the spot that night, right? But the reality is that humans are great at that, identifying patterns across domains, across topologies, across ontologies. But computers are really, really bad at it. So we have to help computers by restructuring data, engineering knowledge, such that we can reformat it into one of these multiplicity of different states, relationships, structures, and allow those patterns to be recognized more readily. For example, if I wanted to figure out how much time, on average, an individual is speaking to another random individual, the driver's license isn't going to tell me that information. But the graph's not going to tell me whether or not somebody has a criminal record, right? So bringing information together to understand the holistic match that we're trying to ascertain is all an integral part of it's really the core of what knowledge engineering is all about. So a lot of these computations are challenging, right? Knowledge engineering, while not difficult in the same way as pattern recognition, still has a lot of challenges around it. And so we use a variety of different tools to try and solve for that problem. So we have solutions across hardware and software. So the first, I'll do a little bit of self-promoting, but we developed the Valkyrie Mark I. The Mark I is a 2U server that we developed from the ground up that's optimized for deep learning testing and then training. The Mark I is really, really cool. We did it actually just for fun, for R&D in Q4. And we did it basically because we wanted to show that people who didn't want to work in the cloud didn't have to. I spend about a quarter of my time as a consultant, as a practitioner, as a scientist, helping companies remove cloud solutions for AI that really didn't work out so well. It's a lot of work. It's pretty arduous. And so creating an environment that's completely customized for them was a really big prerogative. So we developed that box. It's really, really cool. We have a lot more about it on our website. And we did it really as a learning experiment. It's turned out to be really valuable. We also have a collection of technologies. Some of them we already discussed earlier today in the previous talk. We as a firm are moving away from TensorFlow for a variety of reasons, predominantly the lack of customizability and the lack of confidence that Google's not going to try and bring that in-house more aggressively in the next couple of years. For that reason and the fact that PyTorch is now superior in many ways, both from a speed standpoint and from the customizability, our firm is moving towards PyTorch for our deep learning needs. Okay. I promised at the beginning that we were going to talk very briefly about the scientific method and the implications it has on our field. And as it turns out, we fit the scientific method directly within the canonical consulting stages. So anybody who's worked for Booz or Deloitte or McKinsey, Bain, BCG is probably really familiar and probably sick of the research, experimentation, and development phases, or whatever those firms call them. They're all the same concept. We simply injected the scientific method, and we found out that they actually work really well. It's a pretty congruous fit. And our clients, those we work with, the thought leadership that we're building in Austin, is quickly adopting this as the proper approach for implementing real applications of data science within their organizations. It's not waterfall, it's not lean, it's kind of somewhere in between, right? So we have a very direct, very sequentialized process that's waterfall-ish during the research phase. Our experimentation is relatively lean, it's relatively agile, and then we also have the development phase, which again kind of breaks more into a waterfall type approach. We love it. It's been really great for our team, and then also a lot of the practitioners in Austin to adopt an approach kind of like this. We worked on a lot of different types of programs. As I said before, we're practitioners in a horizontal field, not a vertical. So we've done everything from modeling risk for foreign banks to developing behavioral profiling tools for digital experiences, kind of like Fitbit kind of deal. We worked with sales optimization. We work with a company that aggregates the largest publicly disclosed data set around permits and properties in the world. Really interesting firm. One of our favorite clients, actually. We get to work with them to basically make extractions, like what's the revenue of Home Depot going to be based off of how many people were filing for permits last quarter. Really interesting problems. And feel free to contact us. Come down to our lab in Austin. We're right off of Congress Avenue. And visit our website, valkyrie.ai. And any inquiries you have, please email them to inquiries@valkyrie.ai or charlie@valkyrie.ai. The last thing I'll say, this is really important from our standpoint, Valkyrie is as much a consulting firm as it is a thought leadership, a think tank. And one of the things that we're really passionate about, in fact, where the name Valkyrie came from, is the way we champion women in STEM. So half our leadership team is women. A good chunk of our scientists, and the new scientists who are going to be joining soon, are women. We're growing that team very, very aggressively. Some of my personal heroes in the field of data science are women as well, including my two sisters, who are both data scientists at EY and at Palantir, and then some of the leaders of different organizations like Fast Forward Labs, that's also women-led. So if you're a young woman thinking about going into the field of data science and worried that it's dominated by men, it's not the case. You can do a really fantastic job in this field. In a lot of ways, you're better at it than men are. I have to be careful how we phrase superlatives, right? But in any event, be very, very tenacious about it. Have grit. Be excited about the field of data science because there is a really great place for you. And it's a totally new frontier. It's a totally new discipline. And all the antiquated old junk that used to get in the way of women in STEM is really not a part of what comes next.